I can continue. Uh, the Mars Perseverance rover is beginning the science campaign at Jezero Crater, and as you know, it's sort of an alluvial fan from an ancient river that flows into that crater area. So what they're really looking for is signs of ancient microbial life, and if they don't find it directly, they'll store samples for later retrieval and bring them back to Earth. Okay, that'll do it. Neat picture from the Juno mission flying by Ganymede, and this is from 7 June, so just a few weeks ago, and it shows remarkable detail, better detail than we're seeing on the moon, and but the possibility is that some of these faults that you see are actually related to tectonic activity. So if we could ever confirm this, this would probably be the only other place other than Earth that we've confirmed actual plate movement and tectonic activity. Digital door prize. Okay, I saw this that Steve used to do last week and a half ago. At Palomar Observatory, Katie Bauman, who has a number of titles. She's really an electrical engineer and a computer scientist. And she has also received like a courtesy title of a professor of astronomy. She's the one that put together the first image of the black hole in M87 with this Earth Horizon Telescope team. And I've got a link here and we'll put it in the Zoom chat as well. She gave us a phenomenal talk about how she actually put the image together. And the teaser here is that you would think she would have enough data or pixels or resolution to fill in the whole image. But in fact, it was done by interferometry with a limited number of telescopes because they couldn't afford to build their own. So they basically had a very small data set and they had to use computer models to interpret the picture. And of course, the real question is, how do you know which model to use? Because you have a bias of what you'd like to see. So it's a very interesting topic, a very interesting talk on kind of a neat topic that we don't normally get into. And I will tell you that if you put a telescope in space, maybe you'd like to put a telescope on the moon to get a longer baseline, but maybe you want to put one in Earth orbit to create more of these interferometry pairs with Earth-based radio telescopes to fill in the data. Kind of cool talk. Please check it out. We go fairly long on these talks, about an hour and a half, but it's well worth seeing. I like to show an ASIC picture, and this is from Mark of the Witchhead Nebula, and he basically collected the data back in January, and you can see the specs here. But it was done with a reasonably small refractor and a monochrome camera with LRGB filters. A pretty impressive picture, and I'm going to ask Scott to supply me a picture for the next meeting, but I picked this one out because I just like it. Ryan is on, and Ryan is one of our first place science fair winners in the senior division, and the senior division does pretty advanced projects. And I have truncated the title of his talk because it's really pretty involved. He was an 11th grader at Canyon Crest Academy High School at the time of the science fair, and what he did is a really phenomenal bit of modeling work on the evolution of the Cat's Eye Nebula. You know, we've all thought about how does this dynamic stellar explosion and contraction and so forth result in these structures that we see in planetary nebulas. And he's got a pretty good answer from the work that he's done. So at this point, I'll turn it over to Ryan, and then I'll come back after Ryan is finished and introduce our main speaker. So Ryan, I'm stopping the sharing and giving the Zoom over to you.
Okay, thank you. I just want to thank all of you for the award. It's a big honor, and I'm happy to be a new member of the San Diego Astronomy Association. And with that, I'll begin my presentation. Okay, so for my project, I modeled the Cat's Eye Planetary Nebula, which you can see here. Many of you are probably familiar with this nebula. It's a very popular object, and it's one of the most beautiful planetary nebula. And I did this through both morphokinematic modeling, which you can see here, and hydrodynamic modeling. So some background on planetary nebula. Near the end of a star's lifetime, the star begins ejecting its outer layers of gas into space. And the interaction of these layers of gas or winds creates the graceful shell-like structures that we see in planetary nebula today. And until about 15 years ago, astrophysicists believed that they understood how all planetary nebula were formed through what's called the interacting stellar winds model. And the interacting stellar winds model is really great for explaining spherical or bipolar planetary nebula. But when the Hubble Space Telescope was launched, it started taking photos of planetary nebula in unprecedented high resolution. Specifically, with the Cat's Eye here, it showed features like this inner shell and these jets and ANSI. And the interacting stellar winds model was insufficient to explain these complicated small scale structures. So for about the past 15 years, astrophysicists have been doing more observations, numerical modeling, and theory to try to determine how these structures are formed. And for my project, I was the first person to model the Cat's Eye Planetary Nebula, which is one of the most complex planetary nebula, and it doesn't fit in with the interacting stellar winds model. So my goal was to reconcile the Cat's Eye Nebula with the interacting stellar winds model, as well as seeing how it fits in with the newer theories about planetary nebula evolution. So the first thing I did was the morphokinematic model. And you can kind of see that here. Basically, the purpose behind the morphokinematic model is to determine what the nebula looks like in 3D. Right now, we have a 2D image taken by the Hubble Space Telescope, but it doesn't give us a good idea of what it looks like in 3D because there could be visual projection effects and other effects that are influencing our understanding of its 3D structure. So we actually need kinematical data along with the morphokinematic model to determine its structure in 3D. And then once I determined its 3D structure, I then determined a viable evolutionary process for the nebula using hydrodynamic modeling. And you can see that here. The hydrodynamic model basically it tests different evolutionary processes to determine which one is most viable for this particular nebula. I also did a spectroscopy of the nebula myself. And here I am in Julian with my spectrograph and telescope, calibrating my equipment, preparing to take spectra of the Cat's Eye Nebula. And the main purpose of the spectroscopy was to confirm existing measurements of the nebula's electron temperature. And all of the astrophysical modeling was done in the astrophysical code SHAPE, which has been used in over 150 astrophysics publications. And then here are the initial conditions of my hydrodynamic model. And you can see the inner shell, the spherical AGB wind, and then pairs of dense clumps here and here. The ejection of these features from the central star isn't explicitly modeled. Basically, the central star is like a dot in the middle of here, and we just don't have the type of computing to be able to model such large scale differences between the central star and the large planetary nebula. But this starts about 100 years after all of these features have been ejected. And all of these initial conditions are physically justified because and they're physically justified by observations of the nebula in density, temperature, speed, and the age. And these are the results of my morphokinematic model. And here you can see the mesh rendering of it. Specifically, the morphokinematic model reveals the presence of these rings here and their orientation. And these rings of dense gas are difficult to make out on the Hubble Space Telescope image just because of all the reflection and whatnot that's going on. And here we can see my morphokinematic model on the left with the black and white version and then the color version compared to the Hubble Space Telescope images. And then these are the position velocity diagrams that I use to construct and also test the accuracy of my model. The idea behind position velocity diagrams is that if you have a planetary nebula that's expanding radially outwards in all directions. So when you take spectra of a particular planetary nebula, you have about half of the nebula moving towards us and half of it moving away from us. So there's a Doppler shift there. And when you look at a single line, right here I have N2, in high resolution, you can actually detect the Doppler shift on that particular line and see which features are redshifted and which features are blue shifted. And these position velocity diagrams are taken from an online catalog. And so by looking at which features are redshifted and blue shifted and looking also at the Hubble Space Telescope image, I was able to create the morphokinematic model. And I could test the accuracy of my morphokinematic model by generating synthetic position velocity diagrams on the right to compare with the observed ones on the left taken from an online catalog. And then here's an animation of my morphokinematic model in 3D so you can get a better sense of its three-dimensional structure. And then I also made one in color, and it shows all the small scale detail and structure of the nebula as well. And then here are the results of my hydrodynamic model. So on the right here, we have the Hubble Space Telescope image in black and white and my hydrodynamic model on the left. And the corresponding features are labeled. So here we have A, the collimated jets, B, dense clumps, the C, the processing jet remnants or the rings, D, the inner shell, and we can also see the bipolar structure present in both as well. And then here is my hydrodynamic model actually showing the evolution of the nebula. So here are the initial conditions. This is at time equals 0 years in my simulation. We can see we just have the dense clumps and they're shooting out. And then what you see here is a processing jet, and it's creating that ring-like structure that we'll see fully formed there. And then the spherical AGB wind is ejected, which you can kind of see here. It starts to become more visible due to shock excitation and interaction with the ambient medium. And this is about 400 years into the simulation. And that's the end of the simulation at 800 years, right? Or 1,000 years, right here. Okay. And then here are the 4 different views of my hydrodynamic model in density, pressure, speed, and temperature. So my model, I matched the observations with my model in both density, density, pressure, speed, and temperature, so that my hydrodynamic model is physically justified. I also created these position velocity diagrams generated from my hydrodynamic model, and we can compare these to the observed position velocity diagrams on a previous slide. But basically, these tell me that I have the structure and the velocity distribution of the nebula about right. So in summary, this study presents the first morphokinematic and hydrodynamic model of the Cat's Eye Nebula, which is one of the most complex but poorly understood planetary nebula. And again, the purpose of the morphokinematic model is to reveal the three-dimensional structure of the nebula, while the hydrodynamic model reveals a plausible evolutionary process for the nebula. And then, so just some interesting points from my study. The inner shell, which we can, here we go. The inner shell, which is seen in the middle of this nebula, was likely the result of a born-again wind event, because most planetary nebula only have two winds. But I was able to show that a third wind could recreate the structure of this inner shell, which is highly unusual for planetary nebula. Additionally, my study supports emerging theories in the past 5 to 10 years that the more complex structures seen in planetary nebula are a result of a binary central star. Basically, a single star doesn't have enough angular momentum to do things like collimate winds and generate strong magnetic fields that can create the very complex structure that we see in the Cat's Eye Nebula. And this is what a binary central star would kind of look like. And we can see the mass transfer and the Roche-Lobe overflow here within a accretion disk. Planetary nebula are important because they are the fate of all low to intermediate mass stars. And actually, our sun will one day become a planetary nebula. And that's the end of my presentation.
Hey, Ken, you're muted.
You muted me. It's okay. Ryan, that was an impressive presentation, and we certainly impressed when we viewed your presentation virtually at the science fair this year. Where are you going to school next year?
I'm actually a junior, so I don't know yet.
You don't know yet. Where would you like to go?
I'm not entirely sure. I'm interested in pursuing physics as a major, so any school with a strong physics program.
Okay, so we thought you were a junior last year, and okay, so well, you know, there's some great schools, and if you need a recommendation from SDAA by virtue of your science fair work and your outreach, please let us know. Any questions about the presentation?
Yeah, Phil Blanco here. I've got one. By the way, look into UCLA astrophysics. I think you might find a good home there. They love this stuff. I was curious just about some of the mechanics. What software did you use to do the modeling? And then also what software did you use to get the beautiful rendering that you did with 3D color transparency, and you were actually able to move the model around in real time. So that was very cool. So what tools did you use for that?
Yeah, so I used the astrophysical software called Shape, and it's mostly used in morphokinematic modeling of planetary nebula, but it also does have a hydrodynamic function, and it allows you to create like the 3D color models that I showed.
Cool. All right. Well, you did a lot of hard work, so I'm glad that there was something kind of off the shelf that you could use for that.
I have a question.
Go ahead.
Yeah, go ahead.
What happens if you run your simulation into the future past the 1,000 years that you did on to the structures? Did you play with that at all?
Yeah, so basically what happens afterwards is the nebula just keeps on expanding. I don't add any new features, obviously, after the simulation's over, but it would expand. Eventually, it would cool and become less bright. Basically, the lifetime of a planetary nebula is typically around 40,000 or 50,000 years. So at about that time, the planetary nebula would start to cool and kind of disappear into a cloud of gas.
Okay, so you don't have enough data input into the model to give you that end stage physical process in terms of what would you know, all the how things would decay at that point, whether it's through momentum or transfer out, or heat transfer out, or whatever.
Yeah, we don't have any data, obviously, in the future. All we have is data of what the planetary nebula is now, the density, temperature, speed, and whatnot.
Right, but the assumptions about it going away, you know, the matter dissipating essentially into space, right? I mean, that's what ends up happening.
Yeah, generally that's what happens with
Right, but do you have enough data built into the model to let you, complexity built into the model to let you see that if you run it for 10,000, 50,000 years?
Yeah, it
So
will
show that,
calculate that and provide a plausible outcome at that time.
Oh, okay. Thank you.
More questions? If roughly half of the stars are binary stars, and you modeled a binary star, a planetary nebula that resulted from stellar collapse of a binary, but in the case of a single star like our sun, how asymmetrical should we expect all of these shells to look like?
Well, it's because it's a single star, it can only have very slight deviations from spherical symmetry. I would expect the structure of the sun's planetary nebula to be a sphere or maybe slightly deformed sphere. There are a lot of spherical planetary nebula, or mostly spherical planetary nebula, and I would expect it to resemble those.
Okay, I've always been a little bit baffled by asymmetries in stellar mass and so forth, because you sort of assume that a given star, even a rotating star, has got, somewhat, similar, somewhat a consistent material and energy and processes and so forth. But sometimes that's not the case then.
Yeah, sometimes it isn't. But generally, theoretical studies and numerical modeling studies have shown that single stars just don't have enough angular momentum to generate large deviations from spherical symmetry. Because if you have more angular momentum, you can do things like mass transfer and create an accretion disk that can, for example, create really strong magnetic fields that can collimate in certain directions and create deviations from spherical symmetry. But with a single star, it just doesn't spin fast enough and have enough mass to be able to create those large deviations from spherical symmetry. Very slight deviations, but not large deviations.
So it's largely going to do a symmetrical puffing of energy in and out, and this pumping effect that leaves you with all these ring structures.
Yeah.
Any other questions? Well, thank you for making this presentation, and thank you for your project, which we've only seen a snapshot of what you actually did in the meeting tonight. But when the judges all saw what you'd done, we recognize this as a pretty advanced idea and a pretty advanced concept. So this isn't like digging in deeper and more finely. This was kind of an expansive idea, and really thank you for your work. And if there's anything that SDAA can do for you, please let us know.
Definitely. Thank you for